to be minus 2x minus 1 minus 2y minus 1 plus 4z minus 1 is equal to 0. So partial derivatives, primary equations, evaluate at the point, the u and v values at that point. Cross product to normal. Then dot product of x, y, and z minus the coordinates of that point. And there's your equation. Questions?
That doesn't seem like something that should be in multivariable.
Oh. But it involves several variables.
Not hard enough. It just doesn't seem like everything. Okay.
I need to compensate for the exam.
I think what he's trying to say is, what's the catch?
Oh.
Yeah.
Wait till it's on the test, though, man.
Yeah, give you some monstrosity to differentiate. What?
He's gonna say that on the test. It's no use, you know.
All right, I'll make sure the next test doesn't have anything like number 6.
You're a saint.
Or number 11. Even
No.
though it was a bonus, it was still insane.
Yeah, you do that.
To integrate?
To integrate was awful. To set up was not bad.
Once you know how to set up number 6. All right. Okay. Because a lot of the problems in third exam are naturally going to involve integrals over curves or surfaces. But it's going to be more about which integral do you evaluate. Can one of the theorems, Green's theorem, Stokes' theorem, help you get an easier integral? Well, because one of the examples in this lecture, in fact, if you integrate it one way, it's actually quite easy. If you integrate the other way, it's a monstrosity.
When are you giving us this exam?
Comes out April 20th. And you will have 9 days. So,
All right.
compared to the nearly month that the second one was out, so
it's going to be easier.
I will try to make it less tedious than the last one. And no, because I admit what I did was I concerned myself with the setup. The problem is interesting to set up from a setup point of view, and a lot of times the setup itself doesn't concern the integrand. So I thought, okay, here I want to integrate, have them integrate over a tetrahedron. So I set up a tetrahedron. It's like, okay, I'll just fill in some integrand. Now maybe I should have put in 1. But what I do is like, oh, I'll just put in x, y, z. How bad can it be? It's linear in each variable, and I didn't go past that point. So, yeah. Whereas some of the other ones were worked all the way through, because and for an integral, once you know that the setup's going to work, you can just slap an integrand in there and call it good from an exam writing point of view.
Yeah.
Now, the humane thing to do is to see how all the steps go. But other problems like Lagrange multiplier ones, those have to be worked all the way out to make sure they're kosher. So. All right. Now, another thing that these vectors RU and RV are useful for is area of a surface. So, if we have a rectangle, say in the UV plane, doesn't have to be a rectangle, but for simplicity we'll make it that. That's being mapped by your parameterization into a surface. Then what you can do to compute the area is you can carve this up into little rectangles. And each one has dimensions delta U and delta V. And each one of these rectangles is mapped, not sure why I made the arrow curve, but whatever, into some patch of a surface. Now, as you make these rectangles smaller and smaller, then the patch that you get here is, I'll magnify it, it becomes closer and closer to a parallelogram. So it's not exactly one, but it's more and more like one as these little rectangles get smaller and smaller. And the adjacent sides of a parallelogram are roughly these vectors. The vector RU times delta U and RV delta V. So these approximate the lengths of these sides, these adjacent sides of a parallelogram. And how do you compute the area of a parallelogram?
Easy. It's just isn't it the cross product?
Yeah, it's a cross product of these vectors that make up the adjacent edges, and then you take the magnitude of that. So the area of this patch is going to be approximately the magnitude of RU cross RV times delta U, delta V. So that's just the area of, approximately the area of this one patch. So then what you can do is add up the areas of all these patches, and you have approximately the area of a surface. So you let delta U, delta V go to 0, and what you get is the area of a surface, let's write A of S, is a double integral over this region UV space, which we'll call D, of the magnitude of RU cross RV du dv. So this generalizes the arc length formula for the length of a curve. This is the length of a curve. What you're doing is you're integrating over an interval in t, and so a line segment t is being mapped to a curve. So a subinterval being mapped by a parameterization to this portion of the curve, and the length of this segment is the square root of delta x squared plus delta y squared, which then you can express in terms of your parameterization as square root of dx dt squared plus dy dt squared times dt. So this is a similar idea where instead of using a formula for length, we're using a formula of a line segment, we're using a formula for area of a parallelogram. So what will happen on exam is I have to make sure that if I give you a parameterization of a surface, and you compute these vectors, RU and RV, so that's not going to be terribly difficult. It's a differentiation, in theory. And then you got to compute the cross product, but now the cross product is going to be a function of U and V. And then you have to take the magnitude of that vector, so square root of x component squared plus y component squared plus z component squared. And then that's what you have to integrate in a double integral involving that integrand. So yes, I will make sure that any area of the surface problem, I'll make sure that what you get here for this cross product and magnitude is something that you actually can do within a reasonable amount of time. All right.
How would you define reasonable?
Within 9 days.
Well, okay.